Really glad to have Sasha Spiegelman speaking at our seminar today. I've known Sasha for a long time. Sasha did his PhD at Technion, then he worked at VMware with Dalia Malki and Itai Abraham. And then we met at Novi Research, where we worked on the DM blockchain at Meta. And Sasha then joined Aptos as a co-founding team member. I remember Aptos was just 4 people, and Sasha was one of them. And now Aptos is about 100. It's a big company with a big, fantastic research team. Welcome, Sasha.
Thank you, Lara. Thank you for the introduction. And thank you all for inviting me. I actually don't remember the last time I was nervous before a presentation, but this setup is like very serious to me. So yeah, excuse me, it will take me probably a few minutes to get into it. Last time I presented, I gave a talk in a16z, it was last year, I presented Bullsharks. Today I'm going to talk about Shoal of Bullsharks, and I hope the name will explain himself during the presentation. Yeah, let's start. So this is a joint work with Balaji, Rati, and Zikun from Aptos Labs. Some backgrounds before I jump into it. This is at least my journey in the DAG-based consensus. There are other works, but these are my journey. Like started in PodSeed 2021. We presented like theory how you can take a DAG and order it with zero overhead, completely just by looking at the DAG. Then now in Narwhal, we demonstrate a system how we can build this DAG very efficiently. Then Bullshark, we improved latency by taking advantage of the partial synchronous assumption. And now the new work I'm going to talk about today is Shoal, which improves this latency even further. Let's start with Narwhal. So just some reminder, the two, or not a reminder if you never heard about it, it's also fine. Like I'm not assuming anybody knows nothing about it. But this, as I said, Narwhal is a system to build a DAG, and the two main key points to take out of Narwhal is that first that we made the observation that decoupling the data dissemination from the metadata ordering is the key for performance, meaning that if previously data was disseminated as part of the consensus protocol, here we made the observation we can disseminate the data on the side, provide some proof availabilities into the consensus, and then the consensus only has to deal with the metadata. This unlock a very high throughput and also allow to scale out architecture if you throw more machines and the other machines take care of the data dissemination. Ordering metadata is very cheap. So this is one key observation. The second contribution of Narwhal is actually how to take and really build this very efficient round-based DAG. Okay, so once we have this DAG, we have these 3 protocols, DAG, Rider, Task, and Bullshark. You look at this round-based DAG, and the cool thing about all of them is that you can, out of this structure, you can have a total order with zero communication overhead. Everybody are just there is a protocol, there is a system to build the DAG, but each of the validators has a local view of this DAG, and completely locally the validator can look at this DAG, interpret the edges and the nodes in some way that represent consensus logic, and completely locally no overhead, no extra communication. You just order everything. So this is very cool about DAGs. And here comes the motivation for this work. So this is the graph from the Narwhal paper. We compare here Narwhal with different implementation of hot stuff. This is a latency throughput graph. So the vanilla hot stuff, they're roughly about 1800 to 2000 transactions per second can support. Then if we implemented this idea of decoupling data dissemination from the consensus logic, we improved the throughput quite a lot. But when we use tasks directly building the DAG and ordering the DAG directly, we were able to actually achieve a very, very much higher throughput. And so this is very nice because we want high throughput, but if you look at the latencies, the hot stuff latency was better. So the task, we want both of them, right? So throughput, okay, good, but what about latency? And this was the motivation for the Bullshark work. If you see here, it's kind of the same graph, and this is the Bullshark is going to be in blue here compared to task. We saved quite a bit, 33%. Close to the hot stuff latency now, almost there. The goal in Aptos was to implement this Bullshark and Narwhal. We already currently have Narwhal, we call it Quorum Store. This is our local implementation. I mentioned it one time and then again. And when we started implementing Bullshark, we realized that the latency is going to be worse because what we actually not use hot stuff in Aptos. We use Joltrin, and Joltrin reduced one round trip from hot stuff, so reduces the latency by 33% compared to hot stuff. So then it's actually somewhere here on the graph. So we pay quite a lot in latency, and we didn't want to accept this, so we are starting this research and thinking how can we improve it, and this is the motivation for Shoal. If I need to summarize it in like one sentence, so Shoal is a general framework to take any of these protocols and to add pipelining, leader reputation, and the ability to get rid of timeouts completely. And DAG Rider and Task asynchronous doesn't have timeouts, but Bullshark is partial asynchrony. Bullshark has timeouts, so we're able to completely eliminate timeouts. And and this is how, like with these three features, we're able to improve the latency of Bullshark by a lot. Theoretically, we could apply to any of them, but we are interested in Bullsharks, so we will have a shoal of Bullsharks. I know I already talked about Bullsharks previously last year, but it was I won't spend a lot of time about it, just some overhead. I can explain Shoal in a self-contained manner, but just, I'm going to spend 10 minutes just to give better intuition, so otherwise it's going to be a little bit out of context. So I spent some time to explain like roughly what we're doing in Bullshark, and then it will give better intuition about like the Shoal paper. So this is the DAG. It's round-based, meaning that it advances in rounds. In every round, we have at most one node per each validator, and one of the important properties is that each node refers to n-f nodes in the previous round. We are going to use it for quorum intersection. This is the property. Another important property is that this DAG can grow completely asynchronously, because all you need is, in order to advance around, in order to advance around here and to broadcast this node, I need to receive n-f nodes from the previous round. And by the BFT assumption, we have n-f are always honest. So I will eventually receive their nodes, and I will be able to publish my next node, and this is how it's going to grow. The honest parties can always grow the DAG, even during a complete asynchrony. So this is like one of the features. I will also talk about it more when I will talk about eliminating timeouts. So another property of this is non-equivocation. This is part of how we implement the DAG. So you can think about it. Intuitively, you can get this property if you take each node and you reliably broadcast it. Then the reliable broadcast gives you this property of non-equivocation. One of the properties of reliable broadcast that everybody are delivering the same node. In practice, this is a bit costly, so this is not exactly what we are doing, but we can say you can have some sort of efficient reliable broadcast implementation. In terms of the abstraction, how to think about it, you can think about reliable broadcast just to understand how we get this non-equivocation. So what non-equivocation gives us is that we build the DAG asynchronously, and each validator has its own local view. So this can be a local view of validator 1, this can be a local view of validator 4. You see that 4 already has this node, 1 doesn't have this node because of the asynchronous manner of the network, right? This can happen. But if they both, like in this example, have the node, right? The second validator 2 round 2, they both have the node. The node has to be exactly the same, similar. Everything is exactly the same references, the same metadata for transactions, completely everything. And then if you apply this logic, you actually have the same causal history. By causal history, I mean all the nodes that can be reached from this node, like by a path, right? So the same causal history. This is a critical property of the DAG, and it simplifies a lot when you're reasoning about like the consensus logic of the DAG. So when we come to, we have this local view, we want to order everything. That's our goal. We don't want to send any extra messages. We don't want to look at it and order it. So the way we do it is this is validator 1 local view. We're going to interpret the DAG, and we're going to take the first round is going to be an encore round. The second is going to be the votes round. Again, encore votes, encore votes. For every encore, for the partial asynchronous version of Bullshark, which is the one I'm explaining here, where we have a predefined every even round, we will have a predefined encore. Everybody a priori agree on these two. In the randomness and DAG Rider and the other and task, you need to like elect it in retrospect, not in this one. This is simple. You just a priori agree. And then the goal is going to be to just decide which encores I'm going to order, which I'm going to skip. And then the one that and then after I order this, I'm going to go one by one and order the causal history by the sum deterministic rule. And since there is no equivocation, we will come up, all validators will come up with the same order. We say that a node in a voting round votes for the encore if there is a path. And in the commit rule, we have a direct commit rule. The direct commit rule requires f+1 votes to commit an encore. So in this example, validator 1 looks at his DAG. This is the first encore. Can I commit it? Can I directly commit it? The answer is no. I only have one vote. And f+1 in this case requires f is 1, f+1 is 2. I don't have enough votes to directly commit. However, I can commit A2. I have 3 votes. I can commit. Right? The direct commit rule requires f+1. Where is the subtle part? The subtle part is that, okay, this is what I see. This is not I. Validator 4, this is what he sees, directly commit A1. Now, remember, validators can see slightly different DAGs because of the asynchronous manner of the network. So validator 1 actually didn't commit A1, committed A2, and validator 4 committed A1 because it saw the node that validator 1 didn't see. So we need some mechanism to make sure that even though validator 1 didn't directly commit 1, he will be able to commit it indirectly. Yeah, you need to order A1 before A2. And we are going to use quorum intersection, of course, for this. So we have f+1 rows required for direct commit. And on the DAG construction, each node refers to n-f nodes from the previous round. So together, what we get is that if an encore A is directly committed, all future encores will have a path to at least one vote for A. I will illustrate it in a second. And then all future encores will have a path to A. So here's an illustration. Validator 4 directly commit A1. Remember from the previous example, and then validator 1 didn't have this node. But when we will continue building this DAG, since every node, including A2, has to refer to n-f nodes, in this example 3, so it has to have an intersection with either this, or this. One of them, it has to have an intersection. So f+1 to commit, and then n-f in order to build the DAG. So there will be a path between A2 to A1. And we can, of course, apply the same logic going forward. So this is the kind of main quorum intersection here on this graph construction. And then we will use the opposite direction. If there is no path from A prime to A, then no honest validation directly committed A. So here is the protocol on one slide. And what we're going to do, this is our local view of the DAG. And I think I'm running a bit fast here because I already gave this specific talk here. So I'm assuming there is some knowledge. But again, stop me if it doesn't make any sense to you. Okay? Yeah. So. Okay, so this is some local view of one of the validators. A1 we cannot commit, there is only one vote. A2 we cannot commit, we don't even see this.
So is it like a round-based thing here? Yeah, so
yeah.
Fine, okay. Yeah.
I mean, the DAG goes.
There's only one validator whose block I care about in round 1 they're being committed. Is that right?
Sorry.
There's only one validator whose block I care about in round 1 they're being committed. Is that right?
Yes, we all try to, this is the encore, right? We all try to commit this.
So there's one guy who's the anchor for game.
Yes, yeah. And it's predefined. But then after we commit this, we're going to commit the whole causal history together with it. Yeah. Okay, so A2, there's of course no 0 votes, right? And then A3, finally we can directly commit. We have enough votes. Now, the trick is what I'm going to do is that I need to check. Remember the previous example, somebody might have committed A2, somebody might have committed A1, right? And the logic to check it is exactly what we saw on the previous slide. If there is a path between A3 to A2, then we need to commit it, because it means somebody might have directly committed. Because we said if there is no path, then nobody directly committed. It's okay. In this case, it's okay to skip. And as to A1, there is actually a path. So we need to commit A1 before A3 because, if we had this node and somebody else saw this node, had a direct link here, he would committed it, right? And so if we have a path, it means that somebody could have committed it. We need to order it before. Now, it's also true that if we have a path, maybe nobody committed A1, right? This does never exist for anybody. But this doesn't matter because everything is deterministic and all the causal history is the same. So the only goal is to make sure everybody agree on the same total order. So everybody will, when some other validators will see A3, it will also see a path here because like the same causal history for everybody from A3. So everybody will agree on the order. Okay, and then once we do that, we need to recursively apply the same logic for A1 going back. In this example, this is the first round, so we don't need to do it. And so this was like the main goal, the challenge, how to decide which encores to order, which to skip. So we decided to, I mean, the all validators agreed first A1, then we skip A2, and then A3. And then we are going to go and deterministically order their causal history. So in this example, A1 doesn't have causal history, is the first, so nothing. But then for A3, we're going to go and order, by some deterministic rule, say we go like up, down, and order them like here, and we put him here. Yeah, and that's going to be the entire Bullshark protocol. Again, I'm sorry, I feel it was a bit fast, but I assume there is some knowledge about it. I didn't want to bore you. So, but if we have any questions, like I'm happy to answer. Yeah, Tim.
So remind me, so like the green blocks, is there a designated leader of that round to suggest that block? Or?
Yes. So this is the encore, and we can say that the validator that proposed this encore, we can call him a leader. But it's not a leader in the classical sense. When we build the DAG, the leader doesn't have any specific rule. It's just we interpret his node as the encore. That's the only thing. Yeah.
So is it true that like until A3 is committed to, nobody knows total ordering of any other blocks?
Yes. Yeah. We will only order this. We will only know the order of this once we commit A3. Yeah. Yeah, that's true. Yeah.
So when two blocks are committed in the same round, which could happen, right? And
yes.
In this case, we causally order them.
Yes.
But now, suppose like in the causal ordering, I first select the top block and then the bottom block, but yes. I see the bottom block being committed first and then at the top block. So in my ledger output, like how does it preserve safety? Like,
can you repeat the scenario? Because I mean, remember all the validators agree first on A1 and then first on A3. And when I come to see A3 causal history, we also see the same causal history. So we can apply the same deterministic rule. We will depends on what the rule is. We can decide to start from here or decide to start from here. But this is like all agreed upon from before. It's the same code we are running, right, of how to determine the causal order. Does it answer your question? Yeah? Okay.
Along what Nazrit was asking, for round 5, the top white blocks, do they have a chance to be inserted? And
not here, no, not here. It's a good question. In Shoal, we actually try to address some of these issues. Yeah,
What was it? Can you repeat the question?
What about these two? When are they going to be committed? Because they cannot be committed as part of A3 causal history, right? They're in the same round. They need to wait for the future encore to be committed. Yeah.
And now, if this is the current picture, it's still possible that later A2 will be confirmed?
It might be, but not as an encore. It might. I mean, it depends. So here I didn't introduce the notion of weak links, but we can use weak links and then say that I can refer to n-f in the previous round, but I can also refer, and we call it strong links, the links that we use for this logic. But we can also have like the notion of weak links. And you can refer, for example, from here, you can have a weak link here just to refer to these Orpheum nodes that nobody referred to. So when in the future we will order some encore, this will be like part of the causal history, and then we'll be able to order it as a regular node, not as an encore anymore.
Yeah. So like if I'm just thinking about my own view, sort of this chain. Is it true that like when new blocks get added to it, it's always at the end, or could they go in the middle too?
No, there is no going in the middle. No, you only append there. Yeah. So just to summarize the Bullshark, it's simple. At least in my opinion, there is no view change, no view synchronization. You build the DAG leader. It's leader in the sense that, yes, for your question, we do know who is the validator who is supposed to propose the end call. But when we build the DAG, the leader doesn't have any meaning in the system, right? It's not in any way we depend on him more than the others. So it's leaderless in this aspect. I will not talk today about chain quality, fairness, garbage collection, but we can all achieve it fairly easy on the DAG construction.
Sasha, this is probably one of the things you're going to skip, but one of the things I feel like in DAG consensus talks people never talk about is like how are transactions coordinated across different blocks that are being proposed simultaneously. So
yeah,
how would you suggest thinking about that?
That's a good question. I think you refer to the question where we can every validator propose his own block and we can just duplicate all the transactions. This is your question, right? So we don't tackle it on the consensus level. I don't know how. Maybe if you have some ideas, let's do it. But I really don't know how. And we try to tackle it on the upper level. So in Aptos specifically, we have the notion of PFNs and PFNs, VFN. We don't expose the IP of the validators. We have this protection. So we try to solve it there. So balance it through the public full nodes. And of course, in the worst case, somebody can attack us, but we try to mitigate it on the system level. Algorithmically, I don't know what can be done. It's an open question. Yeah.
Is it also true that if I'm an anchor, I can control the total ordering of blocks before me based on who I'm voting on, or referring to before?
Yes, it's true, because when you know that you are going to be the anchor, and you can choose, you can wait a little bit and say, I don't want to refer to this guy, I'm going to refer to this guy. You can do that, yeah. So I showed this slide again, but I want to switch back to Shoal. So I just remind you the motivation. This was Bullshark, and we wanna reduce the latency even more. So this was the motivation. We want to make it this is hot stuff. We want to make it better than hot stuff, somewhere close to jolting as much as possible. Because internally, this was the consensus we are using. We don't want to increase the latency. We want to at least keep it the same while improving the throughput. So let's talk about Shoal. Let's analyze the latency of the DAG. Let's start with that. So for the encores, the latency is going to be 2 rounds. I propose the encore in this round, and in the good case, it's going to be committed, directly committed here. So we have 2 rounds for the encore commit. If you think about this, the nodes in the voting rounds, they will require 3 because the encore is going to link to them, and then they will be committed here. But if you think about your question, if you think about the nodes in the nodes in the encore round, which are not the encore, they will need 4 rounds. Because they will only be ordered here with this encore, right? So this is one source of latency penalty that we're paying. And the solution that Shoal is going to provide is something that we call pipelining. It's not really pipelining. It's it gives an effect of pipelining. It's not really pipelining in a way we usually think about it. And what I mean is that we will have an encore in every round. So there are no 4 in this picture, right? You're either an encore and you order in 2 rounds, or you're going to be ordered in 3 rounds. That's the first contribution on Shoal, and I will explain. The second one, the second cause of latency is that in the worst case, you don't always directly commit off encores. Of course, you would like to keep directly committing them, but sometimes the encore might be the validator, which is the leader, the validator that proposed the encore might be slow. It doesn't get enough support, not get enough votes, and you don't commit. You will order it eventually, but only after you get here, right? So in this case, so you pay all this latency. If you have a crashed validators, for example, here, you have to skip it. You cannot order it. So you pay. All these are sources of latency penalty. And Shoal is a framework to provide leader reputation mechanism. So the idea of leader reputation is that I can look at the past, I can estimate who are the strong leaders, and I can make sure that I exclude all the rest, and the leaders that I'm going to choose in the future are going to be from these strong leaders. So it's increase the probability of the encores to be actually directly committed. So the idea of leader reputation itself is not novel here. We're actually using it today. This is like even from the DM days we were using it. But it was a bit different because there, if you think hot stuff, jolty in the leader-based protocols, you can use this like a leader reputation mechanism, but it's best effort. It's like from safety point of view, it's perfectly fine if I think that Lara is the leader, but somebody else thinks the team is the leader. We will not reach consensus in the next round. None of you will be able to get enough endorsement, but nothing bad will, like in terms of safety, happen because next round we will try again. Eventually, we'll converge on the leader. Everything is going to be fine. Here, imagine like I think that A1 and A3 are the encores, and somebody thinks that this and these are the encores, like complete mess, right? We are just completely like all the complete different things. So we have to agree on the leaders in order to be able to provide safety. So the challenge here is it's a bit more challenging here on the DAG. Let's see how we do it. So one key property of Bullshark, also true for DAG rider and tasks, but like let's focus on Bullshark. Remember, like 5 minutes ago, we saw this slide. We have the encores. And the first goal is to decide which to order and which to skip. We order this, right? And as part of the safety of the block of the Bullshark protocol, it has to be guaranteed that we agree on the same encores. And in particular, we are going to agree on the first encode that we are going to order, right? One could decide it here, one could decide it here, another one could go like far in the future, couldn't commit any of it directly, but eventually, there will be some path and we will decide to order this first. If this wasn't true, the entire Bullshark safety would be wrong. So we can rely on this property. Like we will agree on the first ordered encode, and this is like the key observation. And if we understand this, the rest of the result is going to be very easy because we are like just going to rely on this. So yeah, this was the key property, and the key observation is that we can go back and reinterpret the DAG deterministically. And what I mean by that, if we look at this example, like if I have this local view of the DAG, I need to go to the future in order to understand that this is the first anchor I need to order. But as long as we all like deterministically agree on this point, we can go back now in time and start reinterpreting this, the DAG again from here, maybe in some different protocol, maybe in some different way. Like DAG is a full information protocol. This is the observation. We can do whatever we want as long as it's deterministic. And as long as we have these points of consensus in order to agree to start something new. It's a bit vague what I'm saying, but now I hope it's going to become clear now. So this is the pipeline algorithm. A priori, we have this like mapping from rounds to leaders. Remember, the leader is the validators that's supposed to propose the anchor. So the way it's going to work is that first we're going to start with a simple Bullshark protocol, okay? We have the anchor in the first round, the anchor in the third round, the fifth round, every other round we're going to have the anchor. And we're going to, and ignore these for now, we're not going to use them for this, for the first instance of Bullshark. So we're going to just run Bullshark, okay? And at some point, we are going to agree that this is the first anchor to be ordered, right? This is just an example. It could be this, right? But the important thing is that all validators agree that this is the first anchor, the Bullshark protocol, this instance of the Bullshark protocol is ordering. Doesn't matter how far in the DAG I had to go in my local DAG in order to reach this decision, we all reach the same thing, and now we say, okay, so what we're gonna do now? Now, yeah, we're gonna go back in the DAG and start a completely new instance of Bullshark from scratch, black box. Like forget about everything you knew previously, forget about it, delete. Just remember that this is the anchor you ordered. Now we are gonna run a new Bullshark instance from here going forward, right? And this is completely safe because we agreed on this point. So our local code says, okay, we agree on this point. Let's start again from the next round. This is what we are going to do. So now the encores, like remember, the encores were somewhere here. Now the encores are here. These are the leaders. Now we are going to treat these nodes as the encores. And we are going to run another Bullshark instance. Again, in this example, we order this one because I want to show you the good path, right? We're going to order like an anchor in every round, but it could be this. And if it was this, the first the anchor we ordered, then we would start the next instance from here. But in this example, we start the next instance from here, and this is how it goes. Cool. So this is pipelining, and what we achieve is now that before we had an encore like every second round, now we have an encore every round, and it's a complete free optimization on top of Bullshark. We didn't do anything. We just it's just a more clever rule of how to order the nodes. So now I think the shoal of Bullsharks will make more sense now. Why the name? Because what we have here is actually a shoal of Bullsharks swimming together. Like, I didn't know the meaning of shoal, but I guess most of you know. It's a group of fishes or sharks swimming together. So, I like this illustration because it's like sharks running in a relay race, passing an encore from each other for one to another, right? So this is like, I think, a cute picture.
Yeah, so question on the sort of this like pipelining of Bullshark.
Yeah.
So in the kind of first case, if you, like in the normal case, suppose Bullshark was committing to anchor in round 1 and round 3.
Yes.
Can it happen when you pipeline it, you're now doing round 1 and round 4 instead because you're doing the 2-4 interpretation now?
Yeah.
So it actually ends up being slower than normal Bullshark? So in like standard Bullshark, it was like 1 and 3, but now when you're reinterpreting 2, 4, 6, you say I can't commit to 2, I have to commit to 4. So
I think I understand your question. You say in the original, let me know if this was the question. In the original Bullshark, let's say we could commit this, and then we could commit this, right? But now with these new tricks, we commit this, and then we cannot commit this, and we will commit this. This is your question? Right. Yeah, it's possible. But if you think about it, what it actually means, it means that the adversary is very powerful. He can play it in a way that is too powerful. If he can do that, he could also, in the original Bullshark, it would make sure you cannot commit this and continue not letting you commit. I can think of DAG structures in which what you say happening, but whether this DAG structure actually makes sense in the real world, is it something that the adversary can actually make happen? I'm not sure. Other than that, it's just like a probabilistic argument. It can go it can go both ways. Yeah. No, it's a good question. We thought about it, and I hope I satisfied a satisfying answer. Yeah. Okay, pipelining, not pipelining, leader reputation. So we're gonna use the same trick completely. This is another nice thing. The way we actually worked on it is that first I thought pipelining is impossible. Then we thought about leader reputation, how to do it, because practically we had to do it. We have really a practical system. This is actually very important for us today because we have leader reputation today. So we said we cannot deploy Bullshark without leader reputation, and it doesn't make sense. So we came up with this solution, and then then we realized, oh, the same thing worked for pipelining. Whether 2 weeks before we were trying to solve pipelining and we decided it's impossible. So that's kind of was a nice thought process for us. Okay, so leader reputation, well, same. We have this mapping between leaders to rounds to leaders. We are running an instance of Bullshark. We decide this is going to be the first anchor to order. Again, an agreement point between all the validators. We are going to study the causal history of this validator, apply some heuristics to understand who are the strong validators, who are the less strong validators. Simple heuristic you can think of is how many nodes did you contribute, or how many times in this causal history you're supposed to provide an anchor but you couldn't, and some things like this. And then based on this information, we are going to deterministically assign new leaders going forward. So before we had some leaders, and we went far into the future to determine that this is going to be the first anchor to order, and then we are going to completely change, but deterministically across everybody, the mapping between leaders, rounds to leaders, and we are going to try again now to interpret the DAG with completely different anchors. And it's completely safe, so I find it kind of cool. And so we changed the mapping. We are going to run another Bullshark instance now. This is if we did only leader reputation, but the nice thing is that we can combine it with pipelining together, right? We can do both. We order an anchor, we reshuffle the leaders, the mapping of the leaders, and we actually start the next instance from round 2 instead of round 3, and we get pipelining and leader reputation with the same trick.
So can you tie these optimizations kind of back to the formal guarantees you might state for such a protocol? So the pipelining, can you say the latency improves by a factor of 2, like in all cases? Or
no, the pipelining reduce. So it depends how much you pay for every broadcast here. Like we do 1.5 round trips, but you could also do it in 1 round trip if you had like more, but you pay more communication. So it depends on your implementation of the broadcast, but it saves you. Remember this? Yeah, what it gives you is exactly that. Here it's supposed to be 4, and now that's 3. In every other round, you switch the 4 to 3. So this stays the same. The latency for this node stayed the same, but the latency of this node improves by 25%.
And so then the reputation, like how would you phrase from the reputation that's going to give you an improvement where?
The reputation gives you a very big improvement under faults. If there are actually faults, it gives you a very good improvement. And yeah, I'm actually going to talk about it right now. Like, yeah, because it gives you even more. Yeah, so I discussed now the algorithmic contribution of Shoal. Now I'm going to talk about the system optimization. And the leader reputation played an important role here. I'm going to talk about it. What we achieve here is that we completely eliminate not completely, let's say from every reasonable scenario, we eliminate the use of timeouts. And I think that's interesting because first, timeouts are very painful. Like if any of you ever implemented a distributed system, like you need to think about these timeouts, too long, too short, like how you monitor them. Like it's really painful. And if you think about leader-based consensus, the timeouts are inherent. Like you cannot get rid of timeouts if you have like a single point of failure. Yeah, the reason you cannot get rid of timeouts is that at some point in the system, you are going to wait for a message from the leader, and this is the only thing that's going to trigger you moving forward. You're just waiting for a message from the leader. If you don't have anything else that can trigger you do something, and the leader is actually crashed, you are going to just stall forever. There is nothing else that can, let's say, okay, let's try something else. Like you can just wait forever, right? And the timeout gives you that. Like if you time out the leader, it likes you see, oh, timeout, let's do something else, right? Without it, you can't. And this is and the reason why it's so inherent in like asynchrony and partial asynchrony is that during like synchronous asynchronous periods, you have these validators. They wait for the leader. So then they wait for some time, right? And they don't know whether the leader crashed or the leader is like super slow. And like if they just wait another millisecond, they will receive the message. And like there is just it's an inherent problem, possibility. It's impossible to distinguish. And this is like most of the difficulty in asynchronous system comes from this from this point, right? You cannot distinguish between crashed and slow party in the system. So this means that leader-based protocol that works in partial synchrony must use timeouts. Okay, and what's the problem with timeouts? So if you have them too short, and the leader is actually good, but the validators are just always impatient and move forward and time out the leader faster than the network delay, then we are going to keep timeouting and you change the leaders, never reach progress, right? So we cannot have too short timeouts. But on the other hand, if your timeouts are too conservative, like you pick a long timeout and the leader actually crashed, you will need to pay this entire latency as a penalty before you can do anything else. And a typical timeout is like 1 second, 1.5 seconds. I think today we use 1.5 seconds in Jolteon, like before we will move to the DAG. And yeah, like think about it. Somebody crashed, 1.5 seconds, system doesn't do anything, just stall, right? Really bad. Yes, in Shoal, we have a way to get rid of timeouts like almost completely. And what we are leveraging is 2 things. First is the DAG construction, and second is leader reputation. So, and the cool thing about the DAG construction is that it advances at network speed and completely asynchronously, right? So remember I told you before, if we have a single point like a leader and we wait for a message, we just wait for the message. There is nothing else that can trigger any other behavior. So the DAG is kind of give you this clock, this triggering. Like you keep advancing around and every time, and you advance around completely asynchronously, no timers, you don't need nothing. And this is my intuition, so I share it with you. And every time you advance around, that's an event that now you can rethink what you are doing, right? And this is something that wakes you up, right? And like, Should I do anything else? And so the DAGs give you this like kind of clock, and we'll just keep building the DAG regardless of this guy is being slow, this is actually crashed, and the DAG is always network speed. We don't wait. We just build the DAG, and if we can directly order this, we'll try this, and we just never wait. Okay, so then let's analyze what is actually going on the DAG construction. So we have three cases. The first is a fast leader, as in this example. When I say fast, it's relative to the others. It doesn't mean that the network in synchrony is any way. The network is completely asynchronous, but it's just faster than the other, meaning that most of them is going to actually receive this node like at the beginning, and then they will point to it and they vote for it, right? So if I'm a fast validator, I will get enough support. It doesn't matter the system as asynchronous, synchronous. Eventually, in network speed, I will get enough support and be directly committed. This is like a very nice property of this DAG construction. If you compare it to the leader-based protocol, Jolty and Hotstuff and PBFT others, and you think about this optimistic responsiveness property, they only guarantee it's not enough for the leader to be fast there. They need the system to be synchronous. And the reason is that even as the leader is the fastest and everything is good, the leader still needs to collect votes, right? If the votes are not coming in the timely manner, everybody else will just view change, right? Timeout and view change. So this is a cool property. If we have a fast leader, we can provide network speed both during synchrony and during asynchrony. For a faulty leader, that's even better. This is perfect. We wait 0 time. We just don't care. We continue building the DAG, right? Like this is what we do. Like we just don't care. Like if it actually a faulty validator costs us 0 in terms. I mean, it's not really 0 because it's much better to have a good anchor here and commit it directly. But if you compare it to the 1.5 second latency that you pay just by waiting before they continue the protocol, we have nothing of that. So we saved here 1.5 seconds. If a leader is faulty, it's faulty. I mean, what can you do, right? But at least we don't pay this 1.5 seconds of waiting to agree on the fact that the leader is faulty. We just move forward. Okay, so this is also very good. Again, if you compare to optimistic responsiveness, faulty leader, 1.5 seconds.
That's where you have like a proof that they're faulty in some way?
No, you don't need the proof, right? The DAG, you just keep building it in network speed.
It isn't committed. Right?
Yeah. You eventually, as in this example, you will not order it, so you do pay some latency penalty, but this is an algorithmic latency penalty, not no timeout that actually stall your progress, right? Okay, the only question that we need to ask, which is like questionable, is what about slow leaders? Slow leader is a good leader, but it's slower than others, so he doesn't get enough votes, right? This wasn't fast, everybody voted for him. This guy is slow. So if we had a timeout, it could be actually good, because then maybe if this guy would just wait like 5 more milliseconds, he would receive this node and will be able to vote for it, right? And then we'll be able to directly commit it, and there is no need to wait like another 2 more rounds on the DAG in order to commit the next encore. So then slow leaders, it's like questionable. It's a trade-off whether you wait or not wait in case of slow leader. Here the leader reputation comes into play, because what will happen is that if you're slow, then you will not be able to make sure that your anchors are committed. The leader reputation mechanism will exclude you. This is how it works. You didn't commit, you weren't fast enough, the leader reputation will exclude you. So it will actually exclude also the faulty nodes, which is also good, but even the slow nodes. So leader reputation will make sure over time that only the faster validators will contribute, will become leaders and anchors, and we will be able to order. One interesting question that you might ask, so I ask it for you, what do we do with incentives, right? Because we want to be fair. Like if the validator is slow, we don't want to punish him. And if we let's say our reward mechanism pay leaders, like as today. Today our reward mechanism pays leaders, right? And here just because I'm slow, you don't, and slow is not absolute. It's slow relative to the others, so you're not gonna pay my rewards. And the answer to this question is that with the DAG, we don't need to reward based on the leaders. There's no notion of real leaders leaders of when we build the DAG. It's enough just that you contributed a node, and that's already good enough. But the exact reward mechanism that we are going to use is still to be done. So actually, if like any of you is like you are the expert here, if any of you is interesting to review it and to help us, we'll be happy. But this is like a flavor. I thought this is like a natural question, and I already like I gave you some like what are we thinking? Yeah, this is just a summary. We defined like a property. We call it prevalent responsiveness. We compare it to optimistic responsiveness. So if you think about what I explained before, right? During synchrony and asynchrony, fast and faulty leaders, we get network speed progress. Where with optimistic responsiveness, you only get network speed progress. Fast leader and synchrony, right? Asynchrony, no guarantee at all, and faulty leader, even with synchrony, you have to pay the timeout penalty. In case of slow leader, in both cases for us, without the leader reputation, we need to pay like 2-round penalty because otherwise maybe we could have like directly commit if we had timeout, and now we need to wait to commit the next encore. But here is the hope is that with leader reputation, it will be very rare. So I have to say something about FLP here, because this is a deterministic protocol, and how come like we don't use timeouts, right? Where is the FLP comes into play here? And of course it comes. So in theory, under a very powerful adversary, which I will show here, we cannot avoid timeouts with a deterministic protocol. Because what can happen is that imagine an adversary that just controls all the network, right? Just none of the encores will get enough votes. Like every time there is an encore, there is a leader, oh, suddenly the adversary is so strong, so it will eclipse in nobody votes, right? And doesn't matter. You have a leader reputation, that's very good in practice, but the adversary here is just, all powerful, doesn't care. Every time it's a different node. Like, so in theory, this can happen, yes. And in order to fight this, and to be on the safe side and to provide these guarantees that we like and provide liveness, what we will do is very simple. Like, so in Shoal, what we do is after x is a parameter, 5, 10, 100, 1000, whatever your favorite number is, well, our validator will just fall back to use timeouts. And then, like, of course, we have the theoretical liveness in partial synchrony, right? But in practice, under all reasonable adversarial scenarios, they will never fall back to timeouts. Like, you will order much faster than this adversary will be able, like, to tweak everything, especially with, like, with the reputation. So I think this is very cool because we can actually run a partial synchronous system without we will have timeout somewhere in the background, but they will not impact anything. So here are the numbers, the evaluation. First, we wanted to compare all these like system improvements, the timeout stuff. So we have the baseline Bullshark is no timeouts. Vanilla Bullshark has 2 timeouts actually. One timeout on the leader round and another timeout on the vote round. The reason we had to have a timeout on the vote round is because the full Bullshark protocol, the quorums there were 2f+1. Because we had to support the fallback. I didn't talk about it at all, but just for the recording, if somebody like asked this question. And so we had to have 2 timeouts there. But for the partial synchronous version, we don't need this timeout. So this is why we have the green line. Just the vote, just the timeout, just the timer for the leader in the vote round, not for the other round. In the anchor round, not for the other round. So and these are the results. Like obviously. Yeah, when we have failures, baseline Bullshark without timeouts is much better because we don't pay this like long penalty every time we have a failure. when we check the no failure case, yeah, this is latency, this is the number of validators, this is the number of failures. Sorry, I had to say it before. But in the non-failure case, you see that vanilla Bullshark is worse, but the green and the pink, it's actually, there's a trade-off. This is the thing about slow nodes, right? Slow leaders. Sometimes it's good to have a timeout just to wait for them a little bit and we can commit them. So it's not a clear, without leader reputation, there is no clear win here, like what is better. But for our next graphs, we are going to consider baseline Bullshark, the pink one, and compare everything against a Bullshark without timeouts because we want to evaluate the algorithmic results. And also because the pink is not strictly better, but better, right? Strictly better here and the same here. So we can use the pink. OK, so this is throughput and latency graphs. So this is Jolteon. And this is the different versions of Shoal. Baseline Bullshark, the green is like the full shoal, blue is just little reputation, and the pink is just pipelining. And you see that throughput, we achieve like 120, around 120 1,000 transactions per second. We didn't try to optimize this too much. This result is about latency. I guess we can push it, like if we did some system optimization, we can push it further. But interesting is just Jolten. This is Jolten, not the vanilla Jolten. This is Jolten when we decouple data dissemination from consensus, we get like around 55. And for latency, you see this baseline Bullshark is the pink, and then both the leader reputation and the pipeline, they both contribute to latency. Together, Shoal, the green one, is actually better than everything. Like they can, it means that they separately contribute, and they're together is like even better. And if you compare to Jolten here, so you see we started from vanilla Bullshark. We started even higher because we had timeouts, but this is like no timeouts vanilla Bullshark, and we are almost like close the gap, which was the goal of this work, to close the gap with Jolten. The thing that we are very nice here in this graph to Jolten, the thing that we don't measure is that when we decouple data dissemination from the transaction ordering, there is some more latency to connect these two components, and we gave this latency for free to Jolten. So we don't measure it, whether for Shoal, we don't need this latency. So the gap is probably even less if there is any gap. Okay, so this was throughput and latency in the failure-free case, and now the last graph is latency in the failure case. Oh, sorry, yeah.
Yeah, so like what kind of a validator are we assuming here? Like, is this a commodity laptop? Like, what is the validator?
Oh, these are very strong AWS machines, yeah. Yeah, geo-replicated, strong AWS machine, 3 different regions. Yeah. I don't remember the specification by heart, but I can check it. Yeah, yeah. Yeah, okay, so, and also it's just the consensus. All this graph is just consensus. There is no execution here, right? This is just consensus, just to be clear. Okay, so this is the latency in the failure case. And no Jolten in this graph because when there are failures, like nothing was reliable there because we actually wanted to try it with like a lot of failures. So Jolten was like completely useless. And yeah, and you can see that obviously Shoal with leader reputation like is much better. Yeah, it's kind of obvious because it like excludes the faulty leaders and runs without them. Okay, so bottom line for the numbers for Shoal, so throughput 120K on our consensus only Aptos implementation. Yeah, and I said we could push this number higher. It wasn't the focus. But compared to Jolten on top of Narwhal, we get 2x improvement. Latency again consensus only, we get sub-second latency. Compared to vanilla Bullshark, it's a 40% improvement without failures, and with failures up to 80%. And then compared to Jolten, when we have high load, we get much better latency. And this is because when we have high load, we cannot support the throughput, and then the throughput start impact latency, right? So obviously, if you have high load, the more throughput you can support, your latency is lower. Otherwise, you just need to wait a long time before you even can enter into the system, right? And comparable under low load. And yeah, this is just the slide I like to show. And papers are online. And I always I like to say good stuff about decentralized fault, the TIES blog. And yeah, we also have a blog there about like DAG-BFT. And if you can go there to read like the high level. And for the recording, this is my email. And if any questions, anything, just reach out.
So what's deployed like right now? What's like running on mainnet right now?
Yeah, so what's running right now on mainnet, this, for the consensus, we still run Jolten. And we have our own implementation of Narwhal, which we call Quorum Store. And the way it works, Quorum Store is a very simple component. I mean, nothing is simple when you actually build it, but I mean, conceptually it's simple. It's the data you disseminate, each validator in parallel disseminate the data and gets enough signatures back in return. Holds the proof of availability. Each signature promises that if I sign to you, I promise you I'm gonna hold this data, persist this data in my local database storage until the expiration time. And then the validator takes this proof, push it to consensus. Here is this extra latency I was talking about. And then Jolten will order these proofs. And then before execution, we're going to look at this proof one by one. Hopefully, we will have all the data locally, because in the DOOT case, we just, we disseminate data to everybody. We should have it. Otherwise, we look at the proof, we look who signed it, and we'll go fetch it and then execute. And this is what we currently have. As the plan is to, well, in the final processes of implementing Shoal. But the way it works, you have to implement, then you have to test it, then you have to test it again, then you have to test it again, then to deploy, then you have to test it again. So it will take some time before we can actually launch it on mainnet, but we're on track, yeah. Hopefully sooner than later. All right, thanks.